Hello, very good morning. This is Lakshmi Narayana Gupta Koralla, and I'm working in a Starbucks as a senior data engineer. I have a total like 14 years of experience in IT industry. So today we are going to talk about data ops, accelerating digital transformation through data-centric methodologies. Okay. Here, the evolving software development landscape, organizations are increasingly recognizing data as a strategic asset rather than merely an operational byproduct. This paradigm shift has a new methodologies that bridge the traditional gap between data management and application development process. The emergence of data-oriented application development represents a significant advancement in this direction, offering a comprehensive framework that integrates data engineering principles with software development practices. As its core, DataOps extends the collaborative principles of DevOps, encompass data-centric operations, creating cohesive ecosystem where data pipelines are treated with the same rigor and automation as a core deployment pipelines. Okay, this methodology encompasses automated data pipeline construction, continuous integration and deployment for data workflows, robust data governance frameworks, cross-functional collaboration, and comprehensive monitoring systems. The significance of data ops lies in its ability to address several persistence challenges in modern application development. The need for the high quality data delivered at speed, alignment between technical and business stakeholders, and the increasing complexity of data ecosystems, cloud environments. As organizations prioritize data driven decision making, adopting data ops has transitioned from competitive advanced to a business necessity. This examines the theoretical foundations, implementation strategies, and measurable outcomes of data ops methodologies across various organization contexts. By analyzing both technical and organizational dimensions of data ops adoption, this study seeks to provide a comprehensive understanding of best practices, common challenges, and the future directions in this rapidly evolving field. Okay, the next one, evaluation of the traditional data management. The devaluation from the traditional data management practices to data ops follows a trajectory parallel to software development's journey from waterfall methodologies to agile and DevOps approaches. The traditional data management relied heavily on centralized data warehousing with a rigid extract, transformation, and load, which is called ETL processes, creating significant bottlenecks between data generation and utilization. These legacy approaches, predominant through the early 2000s, were characterized by siloed teams, manual handoffs, and lengthy development cycles that could span months or even years for complex data initiatives. Next, the big data era. The big data era. So the exponential growth in data volume, variety and velocity brought about by digital transformation initiatives exposed the limitations of these conventional approaches. The emergence of big data technologies in the mid 2000s provided new technical capabilities but simultaneously introduced additional complexity in data pipelines. Next, DevOps revolution. An organization struggled to derive timely insights from their expanding data assets. A new paradigm became necessary to accommodate both the technical requirements of modern data architectures and the business need for rapid iterative value delivery. So the next, the data ops emergence. The data ops organically around 2015 as practitioners began applying lessons from software engineering represented a technological shift and the fundamental rethinking of how data teams operate, collaborate, and deliver value. So according to the recent industry research, organizations is implementing data ops methodologies have reported up to 70% reduction in data deliveries and data related defects. This marked improvement in efficiency and quality underscores the transformative potential of data ops in contemporary software engineering practices. Next, So what are the fundamental principles of DataOps? The conceptual framework of DataOps is built upon several foundation principles that collectively enable efficient, reliable data operations. So here the first one is automation and orchestration. So DataOps emphasizes automating repetitive tasks across the data lifecycle, including acquisition. Transformation extends to orchestration, coordinating multiple data processes and workflows to ensure proper sequencing and dependency management. So next, that's a CI/CD for data. So it's a continuous integration and continuous delivery for data. So similar to code-focused CI/CD, this frequently integrating data changes, automatically testing their validity and impact, and deploying them to production environments through standardized processes. Next, version control and reproducibility. This advocates for a version control of logic and analytical models. This versioning ensures reproducibility, the ability to recreate any previous state of the data ecosystems. Next, quality by design. Rather than treating quality as an afterthought, DataOps integrates quality validation pipeline. So implementing automation testing and monitoring to detect anomalies before they impact downstream consumers. So these four interconnected principles create a foundation for efficient, reliable, and scalable data system that can quickly adapt to changing business requirements. Next, it's a core components of DataOps architecture. So the core components are monitoring and observability. So comprehensive monitoring extends beyond infrastructure to encompass data quality, lineage tracking, performance metrics, business outcome alignment, and self-healing capabilities. Implementation typically involves specialized data observability tools complementing traditional infrastructure monitoring, often employing statistical methods to establish standard patterns and detect anomalies. So the advanced teams implements observability as code, ensuring monitoring evolves alongside data systems to maintain visibility during architectural changes. Next, it's a cross-functional collaboration. So DataOps requires collaboration across traditionally separate domains. The data mesh paradigm has emerged as an influential model for organizing teams around data domains rather than technical functions. Other effective structures include DataOps centers of excellence, data product teams, and build models. Successful collaboration frameworks share clear ownership definitions, service level agreements, documented interfaces, and regular synchronization mechanisms. Next, data governance frameworks. The modern DataOps implements governance as code, so where the policies are codified, version control, and automatically enforced within pipelines. The key components includes automated metadata management systems, policy enforcement engines, self-service government tools, and granular access controls. So implementation follows a federated model where the central teams establish frameworks while domain teams define specific rules relevant to their data domains. Next, CI/CD integration for data workflows. The continuous development for data workflows adopts software development practices to data operations. This integration encompasses version control for the pipeline components and automated code correctness and data quality testing and controlled deployment strategies like blue-green or canary releases. So the data-specific CI/CD pipelines include additional impact analysis and continuity testing stages with specialized patterns like the expand contract approach, enabling non-breaking schema changes. The data pipeline automation mechanisms. So the data pipeline automation forms the foundation of DataOps, transforming manual processes into streamlined workflows. Modern implementations leverage containerization technologies like Docker for consistent environments and orchestration tools such as Apache Airflow, Perfect, and Dragster for defining complex workflows as a code. So specialized tools for data transformations like depth and stream processing frameworks such as Apache Kafka addresses specific needs. At the same time, cloud providers offer managed services. This simplify implementation with pre-built connectors and serverless execution models. So DataOps architecture integrates these components into a system where data pipelines receive the same engineering rigor as application code. Modern implementations use the containers to simplify deployment while enhancing scalability and resilience. So the next one, the implementation strategies and best practices. So here, the organizations must cultivate a data-driven culture with a psychological safety that encourages experimentation. The cross-functional literacy and the clear data product ownership models are essential prerequisites for eliminating orphaned data and ensuring proper stewardship across the data lifecycle. So effective implementations follow a phased approach. So far, there are assessment phase, pilot phase, expansion phase, and maturity phase. So now we're talking about what are the different phases involved here. The assessment phase, it caters like benchmark capabilities, identify bottlenecks, establish baseline metrics, and define success criteria aligned with business outcomes. It selects a high-value use case, build essential capabilities while delivering results, and create proof points for stakeholders. And the next expansion phase. So in this expansion phase, we extend implementation across priority data domains, develop repeatable playbooks, and the next, it's a maturity phase. So establish continuous improvement processes, benchmark against industry standards, and maintain alignment with the strategic objectives. So the successful DataOps requires executive sponsorship as a strategic business initiative, not just a technical project. It's not just technical project. Cultivate a data-driven culture with a clear data product ownership and accountability frameworks. So the organization frequently encounter challenges with legacy system integration, skill gaps, governance concerns, and cultural resistance. The successful implementation addresses these abstraction layers for legacy systems, cross-training programs, automated compliance checks, and change management initiatives, emphasizing education and early wins. The next one is measuring DataOps success. So we can measure the DataOps success in the 4 different elements. It's a pipeline performance, data quality, and time to insight and resource utilization. So there is 65% improvement in build success rates and deployment frequency through automated workflows and continuous integration processes. So the data quality, so we have like 48% enhancements in data completeness, accuracy, and consistency through systematic validation protocols and automated testing. So the time to insight, there is a 70% reduction in analytical cycle times, dramatically accelerating decision velocity and build responsiveness to emerging opportunities. And the resource utilization, so there is like 42% improvement in infrastructure efficiency and cost optimization through intelligent workload management and cloud resource optimization. Measuring the DataOps success requires a multi-dimensional approach balancing technical metrics and business outcomes. The DataOps maturity model provides the structured framework for evaluating capabilities across 6 dimensions from ad hoc level 1 to optimized level 4. Next, economic implications of DataOps. DataOps requires that capture direct financial impacts and broader value creation. So these frameworks analyze implementation, operational, and transition cost against a structured benefit taxonomy. Beyond simple ROI calculation, leading organizations employ sophisticated economic models, including net present value analysis and real options valuation, to accurately capture the full economic impact of DataOps initiatives. So the DataOps enhance operational efficiency through process automation, which can reducing manual effort by 40 to 60% for routine tasks, and error detection, which is following the shift left principle to minimize the costly remediation. Next, that's resource utilization optimization, so particularly in cloud environments, and reduced overhead coordination. So it is decreasing the meetings and status communications by up to 30% through transparent, automated tracking. The global DataOps market size was valued at approximately $2.1 billion in 2023 and is projected to reach $10.5 billion by 2030. So the long-term sustainability derives from self-reinforcing improvement cycles rather than one-time efficiency gains. Critical aspects includes technical debt management, which is a systematically addressed suboptimal solutions, knowledge preservation, which is reducing organizational dependence on specific individuals, and economic adaptability, rapidly adjusting to changing business requirements and market conditions. Next, DataOps emerging technologies. Here, the integration with artificial intelligence and machine learning workflows. So the convergence of DataOps and AI ML workflows has led to integrated practices, often termed AIOps or ML-enabled DataOps. The key integration points include future store that detection capabilities that identify when, and explainability frameworks that trace predictions through models to underlying data transformations. Next, edge computing. So the edge computing introduces unique DataOps challenges requiring specialized approaches. These include efficient data filtering and aggregation, intermittent connectivity management through store and forward architectures, and model deployment mechanisms that can package and verify AI ML models across heterogeneous edge environments. The real-time data processing challenges and solutions. The real-time processing requirements have driven significant innovation in the DataOps methodologies, stream processing architectures using technologies like Apache Kafka and Flink. From the foundation, typically employing Lambda or Kappa patterns. Advanced implementations addresses state management challenges through distributed state stores, implement sophisticated back pressure handling, and employ specialized testing methodologies like chaos engineering. And next, so the impact of cloud native architectures. The cloud native architectures has transformed DataOps implementation patterns, shifting focus from infrastructure management to service composition. Serverless computing, containerization provide consistent execution environments. While infrastructure as code has become standard practice. So the multi-cloud strategies introduce additional complexity addressed through metadata-driven architectures that separate logical data flows from physical implementational details. Okay, and then next slide. So the ethical and regulatory consideration. So here, the first one is the data privacy implications. So the DataOps practices directly impact privacy protection capabilities. By design principles increasingly influence implementations with requirements like data minimization, and integrated directly into pipeline specifications. Advanced techniques, including dynamic data masking and homomorphic encryption, have become standard components in privacy-conscious toolchains. The modern consent management tracks permissions as metadata following alongside personal data, while jurisdictional routing capabilities dynamically apply different processing rules based on data subject location and applicable regulation. Next, regulatory compliance. Effective strategies employ unified frameworks addressing common principles while handling jurisdiction-specific requirements through configurable rules. Organizations implement geofencing capabilities to enforce data residency requirements, automated lifecycle controls for consistent retention management, and comprehensive lineage tracking that documents each transformation and access to regulated data. And next, ethical processing. So the ethical considerations have gained prominence as organizations recognize the potential for unintended consequences from automated systems. Bias detection and mitigation capabilities are increasingly incorporated into pipelines, with fairness metrics integrated into data quality frameworks. So the transparency mechanisms have evolved beyond the technical documentation to include accessible explanations for different stakeholders. While continuous ethics monitoring systems compare current processing behavior against baseline parameters to detect ethical drift. Next, accountability. So it extends beyond specific regulatory concerns to broader governance objectives. Impact assessment frameworks are integrated into workflows, particularly for high-risk applications. Organizations implement human-in-the-loop checkpoints through orchestrated approval workflows, documentation automation to maintain accurate operational records, and vendor assessment controls that provide consistent governance across the entire data supply chain. Okay, next one, real world applications of DataOps. So there are plenty of services using the DataOps applications. The first one we can talk about financial services. The organizations undergoing digital transformations have leveraged DataOps to modernize legacy systems while maintaining business continuity. Financial institutions like JP Morgan Chase have implemented DataOps to consolidate disparate data sources, enabling real-time fraud detection and personalized customer experiences while meeting stringent regulatory requirements. And the next field is healthcare. The healthcare providers have adopted DataOps to improve patient outcomes and operational efficiency. Mayo Clinic's implementation integrated clinical, operational, and financial data streams to enable predictive analytics for patient admissions, resource allocation, and treatment effectiveness while maintaining HIPAA compliance through automated governance controls. Next, manufacturing. So manufacturing companies have deployed DataOps production process throughout IoT integration. Siemens uses DataOps methodologies to process sensor data from production environment, enabling predictive maintenance that has reduced downtime by 30% while improving product quality through real-time process adjustments. Okay, and the next we can talk about what is the future directions of DataOps. So the evolving methodology. The first one, like evolving methodologies. The emerging trends reshaping DataOps include declarative pipeline specification approaches that define desired outcomes rather than specific steps, and the contracts that codify expectations between producers and consumers, self-healing pipelines with automated remediation capabilities, and the democratization of DataOps through low-code and no-code platforms that make development accessible to non-specialists. The technical disruption. Several technologies show potential for significant disruption to current practices. The knowledge graphs and the semantic technologies are gaining adoption for complex integration scenarios. Quantum computing presents possibilities for the specific processing challenges. Synthetic data technologies are advancing for privacy-preserving development, and autonomous systems powered by reinforcement learning show promise for self-optimizing data infrastructures. Next, integration with other disciplines. The DataOps will likely see deeper integration with MLOps and DevOps, creating unified frameworks and spanning the entire digital value chain and extending beyond enterprise boundaries. So finally, I conclude that the DataOps represents a transformative paradigm shift in how organizations conceptualize, implement, and manage their data ecosystems. By integrating software engineering principles with the data management practices, DataOps addresses the critical challenges of data velocity, quality, and governance that have historically limited the business value of data initiatives. Mature DataOps implementations deliver benefits across multiple dimensions, which are like technical gains via reduced cycle times and improved quality, economic advantages through optimized resource allocation and cost reduction, and the strategic value creation through enhanced organization agility and innovation capacity. The future evolution of DataOps likely see deeper integration with adjacent disciplines like MLOps and DevOps, increase autonomy through AI-powered self-optimization and expanded scope to encompass cross-organization data ecosystems. For organizations committed to becoming truly data-driven, and DataOps provides not just a framework for transforming data from passive asset into a active driver of business value. So that's all about the DataOps. Thanks for giving the opportunity. And if you have any questions, please reach out to me. Thank you. Have a good day.